Hello, hello. I posted Unit 9, Quiz 2 earlier today, and this is Unit 9, Quiz 1. So we took this quiz several, many weeks ago, and so you might still have it to study. If not, I'm going to slowly go through it, and you'll have it to look back on this one for studying for the test on Tuesday. So number one, what is the correct electron dot notation, or which one is incorrect? Now, again, the big thing here is first you need to know how many valence electrons each have, and alkali metals get one, elements in group 3A get three, elements in group 5A get five, and elements in the oxygen family get six. So the number of dots is fine for each of them. But then the other thing we need to remember is Hund's rule. Electrons spread out where each side is a separate orbital. And so before there's going to be any doubling up, they're going to spread out. So looking at phosphorus, it has five. It needs to go 1, 2, 3, 4, 5. So there really should only be one doubled up. So it should look more something like, if I can move just one of them, something sort of like this. So because this is the one that was not right, we can mark that and say, oh, where's the highlight? I don't know what that does. Where's my highlight button? One highlight. Okay, we don't need to highlight. That's fine. That's fine. I didn't want to highlight anyway. So let me put that back. So C is incorrect. It should not look like that. Okay. I'm at the very least, I'm going to bold it. Yeah, we'll at least bold it. Why is it being weird? Okay, which of the following has the lowest lattice energy? Oh, that's where it went. Nope, still, there we go. Which has the lowest lattice energy? So lattice energy looks at how strongly the positive and negative charges are attracting one another. So how strong is positive to negative? And there are two contributing factors. There's the size of the charge, whether it's plus or minus 1 or 2 or 3. So as this charge goes up, the lattice energy goes up, and the sign doesn't matter. Then the other component is literally the size. So how big is the atom, the ion? So the bigger the atoms are, the lower the lattice energy. So if we're looking for the lowest, then there's the two things we're looking for is which one has the smallest charge, but also the largest size. Now, there should have been one option you could have ruled out right away, because if we're talking about lattice energy, that is for ionic compounds. Here are 4 ionic compounds, but this one's bad. This is a molecule. Molecules don't have lattice energy, so we shouldn't be even looking at ones with multiple nonmetals. So looking at the charges for each of these, we have sodium and chloride +1, -1, plus a negative. Magnesium's +2, chlorine's -1. Potassium's +1, chlorine's -1. Calcium's +2, chlorine's -1. And we don't care about subscripts. That doesn't matter. So of these options, the ones we're going to focus more on are A and C. They're the ones with the smaller charges that'll have lower lattice energies. So of these two, they both have chlorine, but which one is larger in size? So as the atoms get further apart, lattice energy goes down. And we know that potassium is bigger than sodium in terms of size. It's lower on the periodic table. So that is going to make this our answer. Let's highlight that. Yep, that looks nice. Number 3. So dealing with lattice energy, we talked about how it affected solubility, hardness, and melting temperature. And it was inversely related to solubility. So as solubility would go up as the lattice energy goes down. So that's the one showing them inverse. Now, if the question would have said hardness or melting temperature, those two are directly related and would say hardness or melting temperature go down as the lattice energy goes down. And as we talked about lattice energy, that was just simply Coulomb's law. There's not much besides just saying, yep, that's Coulomb's law. And what do we call that type of force that Coulomb's law is showing? And that is an electrostatic attraction. Metallic, I'm missing an L. Oh, thank you. What is not a property of metals? So we know they're thermally conductive, lustrous, yep, they can be shiny. They're ductile and malleable, and they're electrical conductors, but they are not water soluble. Again, if you oxidize, make them charged, they'll dissolve, but not in their normal form, not in their metallic state. Metals are malleable because the metallic bonds are non-specific. That's really important. So as opposed to covalent, electrostatic, where the bonds are very specific, they have to be attached in a very definitive way. Metals, they just need to be near another metal, and that electron C theory allows their electrons to disperse, and that does allow them to be plastic in that they can be shaped. So this is true. So because they have these non-specific bonds, like alloys have to have a set ratio like compounds. Like we might say that calcium chloride has to be CaCl2, but that is not true when it comes to alloys. Alloys, they're mixtures. They do not have to have a set ratio. So this one is false. So they have non-specific bonds. They don't have like this many calciums to this many chlorines. That ratio can vary. Which one is not correct about metallic C theory? So electron C theory, that's good. So yes, we called that the electron C theory, the fact that the electrons can move about. Yes, it's not limited to the octet rule because metals have those many of them have those d orbitals, so it can have. It's not limited to just the S and P block. And again, the whole electron C theory is telling us that electrons are able to move about. And so C pretty much says the exact opposite of D. So C says the electrons are not shared and each atom is holding on to their electrons. That's the exact opposite of what we've said about metals, that they're letting their electrons wander. Okay, which would have the longest bond length? So again, the two main factors here, the two main factors are going to be bond type, whether it's single, double, or triple, and atom size. So with those two, longer bonds are going to come from single bonds, and then as you go from single to double, it shrinks. So single to double, it shrinks. So we can automatically rule out the double bonds. So then between A and C, we have nitrogen versus phosphorus. So the larger atom will give the longer bond, and that's going to be carbon and phosphorus, because we know, oh, I don't like that at all. We know that phosphorus is below nitrogen on the periodic table, so it's bigger. So this bond is going to be longer. Now, 12 says which one is the shortest. Now, if we want to know the shortest, we could go back to these same options and say, well, which one is the strongest? We just need to know which one is the shortest. So which is the exact opposite of the longest? So it's going to be one with the double bond, but also with a smaller atom. So carbon double bonded to nitrogen is the stronger bond, and the carbon atoms have a shorter bond length. How many covalent bonds should we expect nitrogen to have? Now, you might, again, option D said 7. It has 7 valence electrons, seven total electrons, but of those, only five of them are valence. But still, that wasn't the answer. Of those, two of them are paired up. So there's really only three that are unpaired and able to form covalent bonds. So we would expect normally three bonds. Organic chemistry, the study of carbon, we said is everywhere, 80% of all compounds. So why is it so special? And we said, yes, bonds are stable because of how small carbon is. We said, yes, it's versatile. It's versatile in that it can have single and double and triple bonds. And it can bond to a number of different atoms. But what we never said was that there was a whole bunch of it. In fact, I pointed out on a chart in the room that in terms of the Earth's composition, it makes up less than 1% of all the elements in the Earth's crust. We talked about just general properties of these types of substances, and we said metals and ionic compounds and alloys, they all have really high melting temperatures, and they vary. But if you're going to be looking at a molecule or gaseous substance, a liquid or gas, it's going to be molecules. They have much weaker forces that hold them together, that hold separate molecules together. Which one are poor electrical conductors unless you dissolve them? Now, both molecules and ionic compounds are poor electrical conductors, so either A or C. However, when you dissolve an ionic compound into water, we say it can then conduct. We call them electrolytes. And so that is the property of an ionic compound. So metals are always electrically conductive. Ionic compounds are only conductive when dissolved, and molecules are never conductive. And alloys and metals are they're the same thing. It's a mixture of metals. Isomers, they have the same molecular formula but different chemical properties. That is very, very true. So take the same number of atoms, rearrange it into something different, you get a completely different substance, and they have different properties. So they don't have the same properties just because they have the same chemical formula. And then what do we call these structures we've been drawing? These are called Lewis structures, and they show all the bonding and non-bonding electrons. Then finally, I asked you to draw an isomer of DMF. Now, maybe you didn't draw an isomer, and maybe you actually drew DMF, dimethylformamide, but you probably didn't. So as long as you made something, regardless, if you made a correct Lewis structure, you would still come up to the right answer. Now, here is what DMF actually looks like. So, and let me point out that with this CH3, these two CH3s this is actually the shorthand for carbon with three single bonds to three separate hydrogens. So it'd be carbon, hydrogen 1, 2, and 3. Same here, but that's just a shorthand. So I told you specifically there were no double bonds, or there were no rings or triple bonds. So if you made a ring, you got this one wrong. So you could draw an isomer. Technically with the ring, but since I told you we're not going to use a ring, if you put one, you got it wrong. So if you came up with this, fantastic. But all your structure needed to have was a nitrogen with 3 bonds, each carbon with 4 bonds, and oxygen with 2 bonds. And you could have put a double bond between this carbon and oxygen, or carbon and nitrogen, or you could have rearranged it a dozen different ways. But regardless, you would have ended up finding that there had to be one, based on the formula, there had to be one double bond for this structure to work out without any rings. So then moving on, what percentage of gold is in a 12 karat gold? So it's on a 24 karat gold system where 24 karat is 100% gold. So if it's 12 karat, that means it is 50% gold. And then what type of fat is considered the healthiest? So normal saturated fats. So first off, saturated fats are considered bad, but technically if it's saturated, there is no cis or trans. So it wasn't going to be though. So you only use cis or trans when they're unsaturated, which means there's a double bond. And it said cis unsaturated introduces a kink, which allows makes them more fluid and it doesn't build up plaques as much. But trans unsaturated, those are the types that the body are bad at breaking down, and they pack together to form plaques very tightly, and it's generally not good for us. So we don't like that. So again, look over your quiz, look over these answers, study this along with the homework in preparation for the test on Thursday, and let me know if you have any questions.